Alright, what's going on, guys? Welcome back to the channel. ErickMed teaches here. Today we're going to be breaking down a chemical and physical foundations of biological systems MCAT section bank passage. Okay, this passage is from the section bank. On the AAMC website, you get all that prep materials. You get the practice exam, you get the section bank, you get question packs, you get a sample exam, whatever the hell. You get all that stuff. The section bank is the most important out of everything because it is the hardest. Okay, these passages are known to be hard. They're known to be hard. Okay, on my real MCAT, like on the real MCAT, and I could test, like a lot of people in Reddit said the same thing. A lot of my friends that are also pre-med said the same thing. Like the whole exam, all of the passages were not like section bank difficulty. Okay, only like 4 or 5 were like section bank difficulty, and then the rest of the passages were like practice test difficulty. Okay, but these section banks are very good practice, very good practice. So we're gonna be breaking this down here. I want you guys to go ahead and read through this yourself. Okay, I'm gonna scroll down, read through this, pause it whenever you need to. Okay, pause it whenever you need to. Read through this passage. Okay, and you're going to answer these questions first, and then I'm going to break it down, and then you see where you messed up, what you thought was confusing, all this stuff. So this is question number 1. This is question 2. Question 3. Question 4. Question 5. And question 6. Okay, so go ahead, guys. Read through the passage, answer your questions, write down your answers, and hopefully you get everything right. And if you don't get stuff right, you'll see where you went wrong. If you were confused in any part of this passage, I'll break it down for you so you're not confused. I'll show you what to do, how to make this crazy ass. See, I can already look at this and see like what the hell, like matrix assisted laser desorption ionization. Like, okay, whatever. Like that's so extra. So write down your answers, all that stuff. I'm gonna be breaking it down now, and hopefully it'll make a lot more sense to you. So let's go. Matrix assisted laser desorption / ionization, Maldi, is a soft ionization technique used in conjunction with mass spectrometry to analyze proteins, protein fragments, and peptides. Okay, what the fuck is this? What the hell is this? Matrix assisted laser desorption / ionization. See, right there, the MCAT is throwing you some bullshit already. Okay, I've never heard of this in all my years of undergrad. Never. I don't even know what the hell this is. So this is something we don't know. The MCAT is throwing this complicated shit here. It's probably not going to be complicated when we break it down, but they're throwing a scary word here, Maldi. Like, what the fuck even is that? But anyways, just keep going. We know that's to analyze proteins, protein fragments, and peptides. You should know what mass spectrometry is. That's pretty easy. But we're not panicking. We keep going. In Maldi, a plate containing the sample, okay, is coated with 2,5-dihydroxybenzoic acid, DHB, structure shown. This is DHB. So a plate which has our sample is coated with this. Cool, nothing really complicated here. And this coated plate, the coated plate is subsequently subject to pulsed electromagnetic radiation whose characteristics are summarized in table 1. Okay, electromagnetic radiation. And this is the characteristics of the radiation they used in this Maldi technique. Don't even look at the table. Don't waste time on the table. Don't waste time trying to analyze these numbers, trying to see a common pattern here. Only when the question asks for it, then we look at the table. Or then we look at figures or tables. Only when the question asks for it. When you're reading through this, spend more of your time really understanding what the hell is like going on here rather than understanding the figures and stuff like that. Only when the question asks, go for the figure. The radiation ionizes the DHB in the setup shown in figure 1. Okay. So this is our tissue. This is the DHB. Boom. Radiation. Ions. Cool. The biomolecules M are adducted by free protons from DHB and form M plus H and M plus 2H ions. Okay, here's 2 plus 1 plus plus one of them, 2 plus 2 hydrogen ions, 2 protons. Okay, it makes sense. The ions leave the Maldi plate due to the effect of the 4.5 kilovolt electric voltage between the Maldi plate and the MS detector and travel a distance of 0.5 meters to the MS detector within the uniform electric field region. Cool. They just threw something at me like that. So, okay, this is important here. We got numbers here. They gave us voltage amounts, they gave us the distance, and they told us that's a uniform electric field. Okay, this is probably something we're gonna have to calculate. They gave us the units here, meters, volts, uniform electric field. So over here, they just threw something at me here, like out of nowhere. And travel distance of 0.5 meters to the MS detector within the uniform electric field region. This is probably gonna be something they're gonna ask here. So they just threw that at me. It just popped out at me. The velocity of the ions is inversely proportional to their mass to charge ratio. Okay, so this is important too. The MCAT loves to use inversely proportional, directly proportional. They like to ask questions like, if this goes up, then what does this happen? If this goes down, then what does this happen? If this gene gets knocked out, what does this happen? If this part of the pathway is knocked out, then this happens. Like, they like to ask those questions. So mass to charge, so velocity of the ions. So the bigger the mass, what this means is the bigger the mass, the slower the velocity. And the smaller the mass, the faster the velocity. Proteins can be fingerprinted using Maldi if they are subjected to proteolytic cleavage before analysis. Makes sense. Proteins, they get cleaved, you know. All right, question 1. What is the magnitude of the electric field used in the Maldi MS imaging device described in the passage? I knew they were going to ask us something that involves these numbers. Cool. Magnitude of the electric field. All right, you need to know the equation. You need to know your electrostatic equations. Those equations are very important for the MCAT and electric field. So the thing about the electrostatic equations is, I'm going to show you this cool trick here, guys. So electrostatic equations, and I believe it was Kaplan that showed me this. Let's see, do they have it here? Yeah, it's this figure, but I think this guy, I think it's in this video. I remember this video, it showed us it. Whoa, look at that guy's hair and beard. Okay, it's a nice mustache. Right here. Yeah, this, okay. Okay, this is all you need for electrostatic equations for the MCAT. Okay, know this figure. All you have to memorize here is memorize the electrostatic force. That's it. That's all you have to memorize. Because from this equation, we can get the electric field equation. From this equation, we get the electric potential energy equation. From this equation, we could even get the electric potential equation. Okay? And all you have to memorize is that to go from electrostatic force equation, this equation, to the electric field equation, you need this, which is electric field equals force over Q. And to go from here to here, you need this, V equals E times D. To go from electric potential to electric potential energy, you need this equation. Ignore the color here. But this is a very good figure, guys. This literally is a way so you can go from any electrostatic equation, you know, any electrostatic equation. If they ask you the fields, force, potential, energy, potential, you're good. You know all this stuff. So you don't have to really memorize. So this is kind of like a cheat sheet here. Know this for any electrostatic question they ask you. So if you know that, then you know your electric field equation. You know the formula for it. You know what to use. Electric field, guys, is the voltage divided by distance. Okay, so we have 4.5 divided by 0.5. That's it. What's 4.5 divided by 0.5? That's 9 kilovolts per meter. And we got our units. We got kilovolts and we got meter. So we don't need to change anything up, all right? No need to go do all this extra stuff and convert, okay? The question is asking kilovolts per meter. Boom. Look for a kilovolt. Boom, kilovolt. meter. Boom, meter. No overcomplicating, no converting, okay? If the question has these units and in the passage they're the exact same units, then you don't convert. So 9. I'm pretty sure that's it. Boom. There we go. Okay, this is the answer. This is the description of the answer if you want an explanation, all that stuff if you want to check it out. Next question. Which reaction leads to the formation of DHB whose structure is shown in the passage? This is DHB. Which reaction leads to the formation of DHB? So how do we make DHB? Okay, carboxylation of hydroquinone. Oh, you gotta know. Oh, okay, yeah, you gotta know your structures here. You gotta know your structures. There's no going around it. You gotta study your OChem. I know, I have PTSD from OChem too. Don't worry. Carboxylation of hydroquinone. Hydroquinone is this molecule, not the carboxyl, not the carboxyl group. Hydroquinone is just OH and then another OH here. So I'm pretty sure it's this one, but let's keep checking. Oxidation of hydroquinone. No, because if we oxidize hydroquinone, we're just going to get ketone groups here, like 2 ketone groups. We're not going to get the whole, we're missing the whole carboxyl group here. So no, not this one. Reduction of benzoquinone. Okay, benzoquinone is the ketone groups here and here. So if we reduce the benzoquinone, we're just going to get the hydroquinone. And we're still missing the carboxyl group in this reaction, so no. Hydroxylation of benzoquinone. Hydroxylation. I'm pretty sure that means just adding hydroxyl groups. So benzoquinone is, yeah, benzoquinone is just the carbonyl groups here. Oh, that's my phone. What the fuck is texting me? So yeah, hydroxylation is just adding hydroxyl groups. Benzoquinone is the benzene ring with 2 carbonyl groups here and one here. We're still missing the carboxyl group. None of this here tells me about the carboxyl group. I need the carboxyl group. I'm pretty sure it's A. Let's see. Boom, let's go. Let's go, let's go. Okay, nice, nice. There's the explanation. Next question. Which experimental feature of the Maldi MS technique allows a separation of ions formed after the adduction of tissue molecules? Okay. Ooh, now they're asking us about Maldi. I knew there was a question going to come up here like this. Okay. Maldi. All right. Separation of ions. Okay. We go here. These are our ions. Why are they separated? Why are they not all together? Why are they not all together here? Why are they not all together here? Why is one all the way here and one down here? Why is this one over here? Okay, let's see. They're asking that. Why is there separation of ions here after we put in these tissue molecules? Okay, the distance traveled by ions depend on the ion charge. No, it's not this one. It's not this one. Why? Because we have a uniform electric field, baby. I knew it. No, it's not this one, okay? If we have a uniform electric field, okay, it doesn't matter because we have the same, field, we have the same electric field going on here. It doesn't matter the charges, okay? Velocity of ions depends on the ion mass to charge ratio. That is a good question. That's a good answer, but I'm not gonna confirm it yet. I'm pretty sure they told us this too. The velocity of the ions is inversely proportional to the mass to charge ratio. Okay, let's see. Time of travel is inversely proportional to the ion mass to charge ratio. This is meaning that a time of travel is inversely proportional to the ion mass to charge ratio. That feels like, oh, that's a complicated one. Okay. That's like something to do like velocity. But they say velocity is inversely proportional, not time. Velocity is inversely proportional, not time. That's okay. This is another answer where this is an answer choice that MCAT gives you. They try to make it complicated. They're trying to overcomplicate shit, so you choose on it. Time of travel. Yeah, that does sound good, but it's not good. It's not correct. It does sound correct, but it's not correct at all. Okay? So no. It doesn't tell us time of travel. It doesn't tell us this. It tells us velocity. Velocity is distance over time, but no, it's not time of travel. That's a hard assumption you're making there. You're saying that the time of travel is it. No, they told us in the past as the velocity is it. Velocity and time are two different things. Velocity is distance over time, but it's not just time. So that's a hard assumption to make. We're not going to go with that. Electric field between the Maldi plate and the MS analyzer is uniform. Okay, cool. They did tell us that. That's in the passage, but it doesn't answer the question. They want to know why the heck is this being separated? This is a correct. Oh God, this is a good question here. Okay, this is a good example too. This is a good example of how the MCAT tries to fucking trick you. This is bullshit. Okay. Yes, this is correct. Yes, this is mentioned in the passage. Yes, this is a correct answer, but it's not the best answer. This is a correct answer, but it's not the best answer. Okay. Also, the field is uniform. Okay. The field is uniform. It's not going to determine the separation. This is a better answer. This is a correct answer. This is a better answer. Okay. So if you chose this one, it's probably because, you were like, fuck. And you just were like, okay, this sounds good. No, this is okay, look, because it's proportional to the mass to charge ratio, meaning that some will go fast and some will go slow. Okay. So if this one's probably going fast as fuck and this one's probably going slow as shit, and it depends on the mass to charge ratio. If they are small, they go faster. If they're big, they go slower. So I'm going to go with B. That was a tough question, but I'm going to go with B. Boom. Let's go. There's the explanation if you guys want to read it. Which laser is suitable for the Maldi technique after its frequency is doubled? Which laser is suitable for the Maldi technique after its frequency is doubled? Okay, let's look over here. These are our lasers they give us. These are the only lasers that are used in the Maldi technique. So, which laser is like these lasers? Which laser is this laser? Which one of these lasers is just like either of these two lasers used in the Maldi technique? So we have to double our frequency here. So what we're going to do here is we're going to double our frequency for each of these, and then we're going to see which one is probably the closest or is a laser that has these characteristics. So laser A, wavelength is 826 nanometers, power is 1.2 milliwatts. Okay. All right. You have to know the relationship between wavelength and frequency. Okay. If we double our frequency, our wavelength is going to go down by a factor of 2. It's going to be halved. Okay. So our wavelength is 826. So if we double that frequency, then our wavelength will be half of 826, which is like, let me check real quick. It's like 400 something. No, hold on. Let me do this math real quick. 826 divided by 2 is 413. Yeah, that's not a wavelength here. So I'm not going to go with this one. Let's check 714. 714 divided by 2 is like 357. No, that's not the wavelength here. So it's not this one. 650 divided by 2. Oh, I think that's 325. Yeah, that's 325. Okay. Boom. This laser, after we double its frequency, we get half a wavelength. Again, it's inversely proportional. They love inverses, apparently, the MCAT. So half of the 650 wavelength here is 325. So this one seems to be right. Let's just check this one just in case. Oh, half of 532 is 266. Okay, this one has a power of 1.5. This one has a power of 1.5. Okay, it's this one because although both the wavelengths are good characteristics, the power for this one lines up with this one, but the power for this one is 2.2. The answer is telling me the power is 1.5. The table says the power has to be 2.2. So this one's not right. It's this one. This one has the 266 wavelength, average frequency is doubled, and this one has the 1.5 power as well. So D. Bang! Let's go, let's go. Next question. According to the data in table 1, okay, boom, as soon as you see this, we're going all to table 1. That's it. Forget everything else, okay? Forget everything else. Just table 1. No need to overcomplicate shit. Table 1. According to table 1, this is table 1. What is one of the values of the electromagnetic energy delivered during one pulse by the ionizing radiation? Okay. By one pulse during the ionizing radiation. Here's power, pulse duration. Okay. What is power? Power, we know, is work over time. Okay, if you want a way to remember this, just think of power. P, think of punch. Think of like you're punching somebody, okay? If I want a lot of power in my punch, I'm going to punch them like as fast as possible with as much work and energy as possible. Okay, if I want a lot of power, that's what I'm going to do. I can have a lot of energy and punch them really slow, and there's barely going to be any power behind that, my punch. So we want the shortest amount of time with the most amount of energy to have the most power. That's how you remember power. Think of like a punch, like a boxer punching. You know, if you're punching somebody, you're not going to do it slow as hell. You know, you're not going to get anything done. So power equals work over time. The duration is our time. We have our time here. But the answer is in energy. Joules is energy. Work, okay, work is energy. Work, the unit for work is joules. Okay, they give us our time here, which is, let's say, like 5 here, 5 milliseconds, times our power. Power is 1.5. It's hard to do it because you're not seeing my notebook right now, but power equals work over time. We have our power, we have our time. So let's say if we use this number here, power 1.5 equals joules over 5 milliseconds. And solving for joules, it would just be 1.5 times 5. And 1.5 times 5 is, I always write it down because I don't know if I'm correct all the time. It's 1.5, that's 7.5 joules. Okay, now let's check for this one because there's 2 here. 2.2 times 2 is just 4.4, and that's not one of the answer choices. The only answer choice that makes sense is 7.5. 1.5 times 5 gives us the energy in one pulse. And if you get a little confused here, they're asking for one pulse. This is the pulse duration. This is how long one pulse is, not how many times the pulse happened. Okay, so during one pulse, 1.5 times 5, simple equation, power equals work over time, 7.5 joules. Let's see. Yes, this is correct. Awesome. Okay, last question. During protein fingerprinting, what reaction occurs to prepare the sample for analysis? I think they told us here something. Okay, proteins can be fingerprinted using Maldi if they are subjected to proteolytic cleavage before analysis. Makes sense. Proteins undergo proteolytic cleavage. How do we break a peptide bond? How do we cleave proteins? It's not through oxidation. It's not through reduction. It is through hydrolysis. That is something you just have to know. You have to memorize that. It's not that hard. If you took biology or biochem, I'm sure they told you that a million times. But proteins are cleaved through hydrolysis. Bam, and that is it. Cool, that's it, guys. All right. Hopefully that wasn't too hard. This one wasn't that bad, honestly. I might have to do another one where it's a little more harder. Yeah, I might have to do another one where it's a lot more harder. Subscribe to the channel, guys. Thank you so much for watching. Let me know what you guys think. Comment down below, you know, if you actually read this and you were like, what the fuck are they saying here? Because that's some bullshit right there. Anyways, comment down below. Let me know what you guys think. Let me know if you guys want another one Yeah, subscribe, do all that shit. ErickMed teaches here. We out.